So it's a pleasure to welcome you all here today for Sean's dissertation defense. And Sean earned his bachelor's degree from UC Berkeley in 2011, master's degree here at UH in 2014, and now is defending his dissertation today. His dissertation is an interesting and impressive mix of SAPHIRA detector technology and its application to a wide range of adaptive optics systems and techniques. And I think Sean has really made major contributions to implementing these detectors and actually getting them observing on the sky in AO applications. In other areas, most of you know that Sean is an accomplished photographer of national and international renown. He also turns out to be an expert in Nissan Xterra four-wheel drives and pushing them to their limits, which I have shamelessly taken advantage of, as I also have done during his time here at UH. Anyhow, with that ado, I'll go on and let Sean proceed to his dissertation defense presentation. Thanks.
Great. Thank you, Don, for the introduction. And as he said, I'll be talking about the SAPHIRA detectors and how we tested them in the lab and then took the best ones to the telescopes and applied them to science. So before I begin, I would like to start out by extending my thanks to a large number of people. I certainly would not have been able to make it this far without the assistance of quite a few people. First and foremost, I'd like to thank my advisors, Don and Olivier, the rest of my dissertation committee, my collaborators at the IFA and at Subaru, and also Leonardo, which is the company that makes the detectors. I'd like to thank the administrative personnel here who have assisted with the huge piles of paperwork I've generated over the last few years. My fellow students for commiserating, and I'd especially like to thank my parents. So, where we're going today, first I'll start off by just giving a little bit of background information about adaptive optics, the SPECKLE instrument, and the SAPHIRA detector. Then I'll talk about the new technologies that we developed and tested, and then how we applied those technologies towards new techniques and some of the measurements that we made. And then finally, I'll talk about some of the future developments that are ongoing and are building upon the foundation that we built. So the goal of adaptive optics is to compensate for the blurring effects of the Earth's atmosphere. Essentially, there's a schematic diagram of this on the right side. You can think of light expanding outward from an astronomical object like a star in a spherical shape, but we're very far away from it. So by the time those spheres of light reach the Earth, we only see a local part of it, and it seems flat. We don't actually see the curvature because the sphere is so large. And so we call that a flat wavefront. And then it passes through the Earth's atmosphere and encounters different indices of refraction due to the turbulence there. And that causes some parts of the wavefront to slow down relative to other parts. So you end up with this kind of warped and distorted, aberrated wavefront when it finally reaches your telescope. And light bounces through your telescope, and it's actually possible to deform a mirror in real time to cancel out the aberrations in the wavefronts and reflatten them. And then you send the light and split it into two paths. One path goes to your science camera, which can be a spectrograph or an actual camera system, and then the other path is your wavefront sensor, and that's kind of mostly what I'll be talking about today. And the wavefront sensor figures out what these aberrations are, and there's various different techniques for doing that one. The one that we use at SPECKLE is a pyramid wavefront sensor, which essentially has a pyramidal shaped piece of glass that splits, and you focus the PSF onto the tip of the pyramid, and it produces 4 images of the pupil. And that's what's shown over here in the corner. And you can figure out how the wavefront has been aberrated by seeing differences in illumination between these four pupil images. So for example, if you have a tip or a tilt, then the PSF is not focused exactly on the tip of the pyramid, and you would end up with one pupil image being more illuminated than the others. If you had astigmatism, then that would cause diagonally opposite pupil images to be illuminated differently from the others, and so forth. These two movies here show the effects of adaptive optics. We're looking at a star. This is an extremely magnified, extremely slowed down video of a star as it looks through the Subaru telescope with no adaptive optics. And as you can see, it's just a giant blob. But then what we do is with adaptive optics, we can actually pull all the light into this very tight core right here, and we've actually saturated that in order to reveal what remains. But the vast majority of the light is right here in the core of this PSF. The four spots around the corners that are blinking are, we artificially generated those for image alignment, so don't worry about those. I'll talk about those a little bit more later on. So this is Subaru telescope where I spent a lot of my time. Here is a Sean provided for scale. And so for friends and family who don't spend every waking moment thinking about telescopes, essentially the way that it works is that the light comes down from above, it hits the primary mirror, it bounces up to the secondary mirror, and then it comes back down again. And at Subaru, it can continue down to a Cassegrain instrument, which is actually pictured above me, or for our SPECKLE observations, we put in a 45-degree mirror and bounce the light off to the side through a hole in the wall into a room on the other side. So if you go to the other side of that wall, you see this monstrosity, which is the SPECKLE instrument. We've been told that this looks more like a particle physics experiment than an astronomy instrument. But essentially what happens is the light comes in through the hole in the wall here, it goes into AO188. AO188 is the facility adaptive optics system at Subaru. It provides preliminary AO corrections. And then we have SPECKLE afterwards, which provides additional corrections on top of that. So it's kind of a woofer-tweeter system. And then SPECKLE also has coronagraphs, and so it can perform the coronography. After SPECKLE, the light goes out to the various different modules. And the visible light goes to the vampires or first interferometers. I will not talk about those again today. The infrared light can go to the Keras integral field spectrograph, HgCdTe, which has actually since been removed and replaced with MKIDS array. The MKIDS is a crazy new detector technology that both detects individual photons and also is able to detect their wavelength. Or the light can also go to the SAPHIRA camera, which is my chunk of this big project. So a little bit of background on the SAPHIRA detector. It is a 320 by 256 pixel with 24 micron pitch, mercury cadmium telluride linear mode avalanche photodiode. I'll talk about what those last few words mean in a second. It's manufactured by Leonardo, which was formerly called Celex, but they've renamed themselves various times. At the right is a picture of the SAPHIRA detector. This entire package measures 24 millimeters on a side. The actual photosensitive area is the black area in the middle. So SAPHIRA is unique from other Mercadtel detectors in that it has this avalanche multiplication option. So in the top right, we have a diagram of how this works. And we have the depth within the detector on the x-axis, and then the potential energy on the y-axis. So effectively, photons come in from the top right. They deposit their photoelectrons in the absorption region. This region is sensitive to 0.8 to 2.5 micron photons. The photoelectrons wander over to the multiplication region, and there we apply a bias voltage across the detector. And the bias voltage accelerates these electrons and causes them to set off avalanches of additional electrons. And by varying the bias voltage across the detector, we can control how many avalanche events occur. And the useful thing about this is the avalanche multiplication multiplies the photon signal, but this is prior to the ROIC, this is prior to your readout electronics, and so this has no effect on your read noise. So essentially, you're multiplying your signal without substantially impacting the noise. So in typical usage, we run a bias voltage of about 1 to 20 volts, and that can, across that rate, at the low bias voltages, there's little to no avalanche multiplication. And in that case, the detector operates as a traditional source follower Marquette-Tell device, similar to, for example, a Hawaii array. But as we turn up the bias voltage, we get more and more avalanche multiplications out of this. And that's what's plotted in this plot here, where we have the bias voltage versus the number of avalanche multiplications. And this plot only goes out to about 10.5 volts, but you can imagine if you took this out to 19 or so, we get a gain of several hundred. And so, for example, if our read noise is, let's say, 30 electrons, if we run a gain of 30, an avalanche gain of 30 or more, then the read noise is equivalent to 1 electron or less. And so that enables the potential for sub-electron read noise and photon counting performance. So the other interesting thing about SAPHIRA detectors, besides the fact that they have this avalanche multiplication option, is that they're designed for high frame rate imaging. And so this makes them well suited for AO type applications where we're trying to freeze the turbulence in the atmosphere. SAPHIRA has 32 outputs, and unlike other arrays, all the outputs are still used when we operate in sub-window mode. So if we only read a fraction of the detector, we can achieve proportionally higher frame rates. So for a lot of our observations, we run the detector at just 128 pixels by 128 pixels and achieve a frame rate on the order of 1.7 kilohertz. So our group is well placed in that we have a great working relationship with Leonardo, the manufacturer. And so they essentially produce the detectors, they send them to us, we test the detectors, and then we take the best ones to the telescopes. During my time here at the IFA, we've gone from the Mark III SAPHIRAs to the Mark 19 SAPHIRAs. The Mark III is kind of a generation, or the Mark number is kind of a generational number. The Mark 19 detectors arrived just 2 days ago, in fact. So this process is ongoing. And during that time, during these development iterations, we've extended the short wavelength cutoff from 1.4 microns down to 0.8 microns. We've reduced the dark current in these detectors. We've reduced the prevalence of hot pixels and improved their cosmetic quality. And then we've also sent several of them to multiple different telescopes. So besides iterating and improving SAPHIRA designs, we developed new readout electronics for operating the SAPHIRAs. This was developed within the IFA. It's called lovingly the pizza box. I think originally it was going to be a square design, and then it ended up getting kind of elongated, so it's vaguely pizza box shaped as opposed to exactly pizza box shaped. This development was led by Eric Wormbier, who did the hardware, Charles Lockhart, who did the low-level software, and then I did a lot of the interface design for this and did the testing. And this replaced the leech controller, which is what we previously had. The leech controller was much slower. So the pizza box is FPGA based, field programmable gate array. And in our typical operations, we run it with a 1 megahertz clocking speed. This is 4 times faster than the leech controller. And the clocking speed controls how quickly we can read images from the SAPHIRA detector. So that corresponds to about 400 frames per second if we're reading the entire array, or 1680 frames per second if we're only doing a 128 by 128 subarray. However, as I'll mention later, we've recently doubled these speeds, but we haven't fully tested that quite yet. So the pizza boxes have been quite successful. They're deployed to a variety of telescopes. We're using them for lab testing here. There's one at SPECKLE, There's one currently in the lab, but will go to Keck this fall. And there's another one at RoboAO at Kitt Peak, which is in the process of being shipped here to Hawaii. And then there's one on Maui at the Solar Telescope. So in addition to iterating designs to the detectors and developing the new readout electronics, we commissioned cryogenic preamplifiers for the SAPHIRAs and used these in order to mitigate some major noise problems that we had. This is a picture of CRYO. I showed it earlier. As you can see, it's a little bit of a mess. And this environment at Subaru is very noisy. There's a large number. The ground is all metal, so they tend to have ground loops. And all these wires hanging on the outside of the instrument end up working as antennas, and we end up picking up noise just from the air. So at the right is a example SAPHIRA image showing what we came to call radio frequency noise. 32 pixels get read out at the same time, and so if there is some kind of voltage being introduced during the sampling of the pixels, it'll cause them to be offset systematically. And so you end up with these 32 pixel raised bars, whereas ideally you would just see a static kind of static noise pattern here. So our read noise in the lab was, we thought, reasonable, but then when we would take SAPHIRA to places like CRYO, we'd see that our read noise was 10 times higher. And that's due to this radio frequency noise. I'm considering the radio frequency noise to be part of the read noise, but you could quibble about that. So at times, so I did a lot of kind of reading into this to try to figure out what the problem was and how it could be mitigated. And I came across the following passage in the book Scientific Charge Coupled Devices. Obviously, SAPHIRA is a CMOS array. It's not actually a CCD, but this quote applies anyway. And I'll read it. EMI and related noise sources are the most difficult and frustrating noise problems to solve by the CCD camera engineer. Solutions are usually panic-oriented and derived by trial and error methods without much understanding given to the physical cause and effect. And I saw this and I thought, this is a 2-sentence summary of grad school for me. But we did try to understand it. We did try to mitigate these problems. I didn't only be panicked all the time. So we adjusted various different grounding setups. And we switched from the normal building ground to a clean instrument ground. We electrically isolated the SAPHIRA camera from the CRYO bench. The CRYO bench is this white frame here. Sometimes there's other things shorted to it. I've put a multimeter to it and seen 50 volts before, which is not good. And we've also done various star ground chassis things in order to mitigate the noise. We also wrapped the wires in foil, which added kind of a festive appearance to the camera. And because of these efforts, we reduced the noise from 10 times the lab value down here in Hilo to about 4 times the value we measured down here. But we wanted to do better than that. Oh, I'm getting ahead of myself. We also, I took into account how the detector spent its time reading the pixels, and then I put together power spectra covering frequencies from 1 hertz out to 500 kilohertz to try to see where the noise was coming in at what frequencies. And initially we saw a bunch of big spikes, and through these various noise mitigation techniques, we reduced it to just having a single spike at 60 hertz, which is where all your household electronics are, and that's not surprising.
Did the foil actually help a lot?
In some cases it did, actually. With the leech controller, the foil had a huge impact. With the pizza box, it initially did, and then we put shields around the cables, and then the foil stopped being very effective at that point because there was already more effective shielding there. So in order to get to better noise values, we collaborated with the Australian National University, and they sent us some cryogenic preamplifiers for the detector, and we tested these and deployed them. It consisted of 2 boards, one of which holds the detector, and that's what's shown in this image here. And then the second board that actually contains the preamplifying circuitry. So this passes through the clocking pulses from the readout electronics without affecting them, and it filters the bias voltages in order to help stabilize them. But the important thing is that it buffered the signals from the detector's ROIC, that's the readout integrated circuit, in order to clean them and enable the longer cable runs out to the readout electronics. We had about 1 meter of cables between the actual detector and our readout electronics, and the ROIC struggled to drive signals across those cables. We'd end up with reflections and ringing within the cables, and then also there'd kind of be drifts and oscillations. The preamps they're basically a drop-in replacement, so you don't need to adjust the dynamic range of your ADCs, so it makes it easy to put them in. So how did these actually perform? So here in the lab, where we considered our noise fairly reasonable to begin with, we actually saw that the preamps decreased the noise by half. That was pretty significant. In these, I'm showing numbers in microvolts. It's a unit that is physical and easier and more precise to get to than electrons. I'll talk about the electron conversion in a moment. But at SPECKLE, which is what really mattered, we saw a 2/3 reduction in the noise. So that's pretty impressive. And this is kind of the before and after of what we saw at SPECKLE. So before we had this nasty RFI, and finally we see the nice staticky detector that we wanted to see. And you might look at these numbers and say, well, this is still significantly worse than HeLo. And I would say yes, but these aren't comparable because this is in a different readout mode. And there's additional noise sources in the SPECKLE value. So if I operate the HeLo setup in the same readout mode, then I get 211 microvolts. And the remaining difference between these two is likely due to the slight difference in temperature. We were operating at 85 Kelvin there and 60 Kelvin here, and that slightly lowers the noise. We went through the charge gain process in order to get an actual measurement of electrons for this. We think this is about equivalent to 55 electrons, which may sound a little bit high if you're accustomed to like Hawaii devices. But this is in read reset mode, which has KTC noise in it. It's an additional noise source that you would not have if you're doing just a regular up the ramp read. And also, again, this is at a unity avalanche gain. So if we run an avalanche gain of 55 or higher, then this becomes equivalent to 1 electron or less of read noise. So the SPECKLE noise, which was previously 4 times the HeLo value, now matched it. And as a bonus of these cryogenic preamplifiers, they enabled us to clock the detector faster. So we went from 1 megahertz clocking speeds to 2 megahertz clocking speeds, which enables a full frame readout rate of 760 hertz or 128 by 128 pixels of about 3 kilohertz. And so I wrote up this and I presented it about 2 weeks ago at SPIE. So in addition to the various hardware things that I've talked about, we introduced new readout modes, new ways of reading the detector. So the original SAPHIRA detector came on a ROIC called the ME911, and that only allowed global resets, where you reset all the pixels at the same time. And therefore, we were forced to do what was called up the ramp readout, or sample up the ramp readouts, where you reset all the detectors, or all the pixels, and then you sample it multiple times at intervals, and then you combine these multiple reads into your image. These reads are non-destructive, so you can read multiple times between each reset. And that enables you to achieve very low noise because you're combining these various different reads to reduce the noise. However, it's because you're doing multiple reads, it's comparatively slow than if you just did 1 read per science image. So this is great for low background applications where your fluxes are low and you have lots of time to integrate, but it's poorly suited for AO applications. So then we received upgraded ME 1000 ROICs, and these were designed by ESO, and they enabled line-by-line resets, and therefore a rolling shutter. And so instead of resetting all the pixels on the detector at the same time, we could reset just one line at a time. And that enabled new readout modes that were better suited for AO applications. So for example, we tested out what we called read, reset, read mode, wherein we read a line and then we reset it and then we read it again. And then we subtract one of those reads from the others. And that leaves behind the flux that accumulated during that time. We saw a settling noise problem during this readout mode. So essentially, whoops. So if this is the image following the reset and this is the image before the reset, they're both dominated by this fixed pattern noise that is intrinsic to infrared detectors, and you always have to subtract images somehow in order to get rid of this. But when we tried this in read, reset, read mode, we ended up with all this extra noise over here, which was basically a settling problem. So we ended up not using this technique once we'd tested it. So then we tried a different mode called read reset mode, where you don't have the read immediately following the reset. And so you don't have this post-reset settling problem. And so you do have a ton of fixed pattern noise in it. And what you have to do is block off the detector, collect a bunch of images with the detector dark, average those together, and then subtract that from each individual image in order to get rid of that fixed pattern noise. And in this case, we saw that it worked better than read, reset, read mode, but there was about a 2-hour settling period where the detector had to kind of come into thermal equilibrium after it started clocking. So the application of this is if you're doing astronomical observations that require good detector stability, you really should idle the detector and just have it clocking for at least 2 hours before you do these observations. And this is a plot of showing kind of the noise versus time that we get in this method. So I wrote this up and I published this in JDIS earlier this year, kind of a full treatment of the noise of all these different readout modes, and also I had talked about a lot of the timings that are involved with the detector. All right, so how do we apply this? I'll talk about some speckle lifetime measurements. So AO corrections are not perfect. And we end up with a halo of speckles around the core of the star that's left over after the AO correction. And these look like a planet. So if you look at this image right here, there's a coronagraph in the middle, which is why you don't actually see the star. You couldn't tell that that dot right there is a planet and not a speckle. And there's been various techniques that have been developed to mitigate and differentiate between speckles and intrinsic structure in your target. This is one shown up here. This is angular differential imaging. And after processing, you can see the planet much more clearly. But this is applied to images after the fact, after you've collected them. The speckles are typically on the order of 1/1000th the brightness of the peak of the star. So in this is basically the same thing right here, except this is the star. This is what it looks like. You just barely see a little airy diffraction ring. In this case, I'm exposing for the peak brightness of the star, and the image is linearly scaled. But if suddenly I increase my exposure by a factor of 10, and then I logarithmically scale the image, then suddenly you see all these speckles here. So this is all in this image, you just don't see it with this linear scaling. And again, these 4 little speckles on the corners, we generated ourselves for photometric and astrometric calibration. So these images were recorded at 1680 frames per second, and they're being played back at about 30 frames per second. Interestingly, what's happening in this video on the right is this is with SCHCAO corrections, which are pretty good. And then we turn off SCHCAO right there, and you see all these extra speckles appear. Because this is the PSF that's being delivered by AO188, the Subaru Facility Adaptive Optics System. So you can really see the effect that SCHCAO is having with the big blobby speckle halo, whereas it can mitigate them very effectively in this image. And so as you can see, these speckles kind of change on a variety of timescales, and I'll come back to that. So the speckles are scattered starlight. So essentially, it's actually possible to apply starlight on top of a speckle and destructively interfere it away. And you can do this in real time, potentially on sky, if you have the right technology and the right techniques. There's been various techniques, various algorithms for doing this. One of them is you basically put a sine wave on your deformable mirror. Your deformable mirror is at the pupil plane of the telescope. So your focal plane, which is where your science instrument is, shows the Fourier transform of that. And the Fourier transform of a sine wave is a delta function. So you get a little copy of your PSF off to the side. And so what you can do is you just generate these speckles all over the place where there's pre-existing speckles. You scan through the phase space and you find the one that destructively interferes it away. And because you're destructively interfering the speckles away, you can actually reduce or you eliminate both the speckles and their photon noise. Whereas if you do this post facto on the computer, as is the case for angular differential imaging, you can remove the speckles but not their photon noise. So this has the potential to unlock much better contrasts than you would otherwise be able to do. And the reason we care about this is if you're trying to find a planet or something, you would be much more able to find the planet in the dark hole over here compared to if it's in the speckle halo. Oh, so this image right here is actually us doing speckle nulling with the SAPHIRA on the SchexAO internal source. This is not on Sky. It's easier to do on the internal source because in this case there's no turbulence that we have to deal with. We ran into various problems with this, so we didn't take this technique very far, but I ended up measuring the speckle lifetimes because it's not really known how quickly the speckles change. And the effectiveness of these real-time speckle nulling loops depends largely on their ability to mitigate the dynamic speckles. So if you have a speckle that's quickly changing, you need to have a loop that is going quickly in order to null out that speckle. And so if you don't know how quickly the speckles are changing, you're going to be hard-pressed to figure out how well your speckle nulling loop will perform. So I performed two different analyses of this. First, we developed a new technique that is directly applicable to predicting the performance of a real-time speckle nulling loop, and that's what's going on here. Essentially, speckles increase, or the contrast increases, basically changes upward in this plot versus time. And we actually went a little bit into the theory of how we would expect the speckles to change. So not only am I doing instrumentation and also astronomical science, I did a tiny bit of theory. So in a second analysis, we repeated the analysis of a technique in the literature, but our data was 3 orders of magnitude higher temporal resolution. And we actually saw a new time scale of speckle change that had never been characterized before. And that's what this little spike is right here in this plot. The previous research using this technique was not sensitive enough. It did not have a high enough frame rate detector in order to see this particular spike here. So we talk about that some, and I wrote this up and have submitted it to PASP. So next, we used SchexAO to observe the HIP 79977 debris disk. This is about a 10 million year old disk around a star. And essentially, it's a baby solar system. You can kind of think about it like that. It's a solar system that's in the process of forming. We used the Keras integral field spectrograph for this. We did not actually use SAPHIRA for these particular observations. Keras covers the J, H, and K bands simultaneously. So what we can get in one shot is 22 wavelength bins, and that's what's shown in this little video here, is us scanning through the wavelengths. And you can see some of them are kind of noisy. You can see the water band pop out right there. But we take these images, we can collapse them down into J, H, and K bands, which is shown in the figure in the bottom left. And then what we did was we performed PSF subtraction using the CLIP algorithm, and then generated 20,000 synthetic disks and propagated them through the same PSF subtraction pipeline as the actual data in order to see how that pipeline affected the disks, or the synthetic disks. And then what we could do is compare which synthetic disk, after forward modeling, matched our on-sky data the best, and we say, okay, this is probably what the HIP 799 disk actually looks like. So this is the best fitting disk here, and this is what it looks like after we've propagated it through the forward modeling pipeline. This is our actual science data, and then we subtract them, and we don't see much structure, which indicates that the disk is a good fit to the science data. So what did we infer from that? We found that the disk was moderately forward scattering. We derived a Hinier-Greenstein parameter G of 0.6. And that essentially means that the dust likes to, it preferentially scatters the light forward. So you can imagine if you're holding up a CD and you're viewing it nearly edge on, the star would be at the center here, and you're not viewing the CD perfectly edge on, but slightly tilted. And the forward scattering causes you to see only the front side of that CD. You don't see the back side of the CD. And so that's why the disk appears to be slightly offset vertically from the center of the star. We found a best fitting fiducial radius of the disk, which is kind of where the number density of particles peaks at 53 AU. We saw that one side of the disk was brighter than the other side, particularly at H band. You can see this side of the disk is brighter than the other ones. We talked about a couple mechanisms that could potentially cause this. Previous observations of this disk had seen a little blob, and they said, well, maybe that's a planet. And our data was much better than these previous observations, and there's clearly no blob there anymore. So we say that that was probably just an artifact of their reduction and not any intrinsic structure. And so we've written this up and we've submitted it to the Astrophysical Journal. So next I'll talk about some of the future developments that are building upon the work that we've already done. So currently in most AO systems, the wavefront sensing is done at visible wavelengths, and the science camera is at near-infrared wavelengths. There's a couple reasons for this. First and foremost, the image quality is better as you go to near-infrared wavelengths, and you want the best quality for your science observation, so you put your detector there. And also, there haven't really existed many options for high frame rate, high sensitivity infrared detectors that are suitable for wavefront sensing. Whereas EMCCDs are perfect for this, but they only go out to about 1 micron. However, there's a lot of interesting targets that have very little emission at optical wavelengths. And you'd like to be able to observe those with adaptive optics, but it's difficult or impossible to do so due to the lack of the ability to wavefront sense at those wavelengths. And these include targets such as M-dwarfs, which are the most friendly targets for if you're trying to find planets in the habitable zones of them by direct imaging. And so, or another example of that would be stars that are embedded in disks. And so the disk tends to attenuate a lot of the short wavelengths of light. So SAPHIRA is a promising technology for doing these sorts of wavefront sensing. And we demonstrated the capability of SAPHIRA to perform pyramid wavefront sensing while at SKEXAO. So I'm going to show a video here showing the results of this test. There's a lot of things going on in this video, so I'll talk about what's going on beforehand. On the top left is the channels of the deformable mirror on SPECKLE. And we're working on the internal source in this case. We're not on Sky. But we have the option of just applying turbulence using the deformable mirror, sensing that turbulence, and then correcting for it. So we can test, we can simulate on-sky conditions effectively. So the panel up here shows what's going to the deformable mirror. And when we close the loop, you'll see the corrections appear here, and they approximately match the turbulence because we're trying to cancel out that turbulence. This viewer on the left is the pupil plane, or the focal plane image viewer. This is an internal science camera on SPECKLE, and it shows basically what the star looks like as it is affected by the turbulence and the adaptive optics corrections. The panel in the middle is the actual SAPHIRA images. So we have the pyramid optics in front of it, and we're seeing the 4 different pupil images. And as the turbulence blows through, you can see the turbulence blowing across the pupils. And then on the right is Olivier's utility for starting and stopping the loop. And he'll do that a bunch of times. All right, so you can see the PSF is affected by the turbulence, and now the loop is closed, and the PSF looks great. It's a fantastic star. And then Olivier goes and opens his loop again, and it becomes all blobby. So this is really demonstrating the performance and the effectiveness of SAPHIRA for wavefront sensing. And it's a cool video besides. And he's going to open the loop again shortly. Open the loop, Olivier.
I'm on it. I'm on it. Faster.
Clicking lots of things, clicking the wrong things. Oh, thank you, Olivier. All right. All right, so partially because of the success of that test, Keck decided to use a SAPHIRA system for their Keck Planet Imager, which is an upgrade to the NERC2 AO system that they have. So at one point, we went up there and we stuck the camera inside the NERC2 system. We got to wear the bunny suits, and we tested to see how the noise was, to see how it compared to Subaru, because we had all these RFI problems at Subaru. We saw that Keck was much worse in the lab, but not as bad as Subaru. And then we also were checking to see if we could actually fit the SAPHIRA camera into their enclosure. And that went well, and they've been developing this since then. Charlotte Bond has been leading the effort here at the IFA, and that will go up to the telescope this fall. So there's 2 additional efforts to develop larger format SAPHIRAs. You could point out that 320 by 256 is not a huge detector. That's what your phone had 20 years ago. Not really. That's what your digital camera had 20 years ago. So here at UH, we're developing a 1K pixel by 1K pixel device. It'll have 15 micron pixels, so it's a bit smaller than the current one. And this will have 16 outputs, so half the outputs of the current detector. And this is really optimized for low background imaging, not speed. And it'll be 3-side close buttable, so you can stick these together into and run multiple images or multiple detectors at the same time. The first devices will arrive this winter. There's a second effort going on. A consortium of ESO, Max Planck, and Herzberg are developing a 512 by 512 pixel SAPHIRA with 64 outputs. And this one is really optimized for high-speed operation and wavefront sensing. The current detectors are ideally suited for kind of the current generations of telescopes in the 8 to 10 meter class, but they're not really big enough for what you'd want for a 30 meter class telescope. And so that's really what the 512 by 512 size is optimized for. So recently, a lot of instruments have proposed to use SAPHIRA systems. And we can't take credit for all of this, but we've certainly contributed towards their success and the desire of a lot of people to start using these detectors. So SPECKLE currently has 2 SAPHIRAs at it. I don't know how long-term this will be. There is a commercial camera called the CRED1 by First Light Imaging, which provides an easy way to get access to the capabilities of SAPHIRA. And so SPECKLE has the CRED1 on it right now, and also our camera there too. The Magdalena Ridge Observatory Interferometer will be using a SAPHIRA for fringe tracking. The Giant Magellan Telescope will use a SAPHIRA in order to phase its mirrors to 50 nanometer accuracy. It has segmented mirrors, and these all need to be phased to 50 nanometer accuracy, which is kind of crazy when you stop to think about how difficult that is. The extremely large telescope will use at least one, probably more, SAPHIRAs for wavefront sensing. In the FRIDA module, which is an extremely forced acronym for infrared camera. But yeah. These instruments were all published their intent in the most recent SPIE proceedings. I'm sure there's other ones as well. I just am not aware of them. So in summary, we've developed, we've tested, we've refined, and then we've deployed to the telescopes several generations of SAPHIRA detectors, the pizza box readout electronics, and these new ANU preamplifiers, which greatly reduced our noise. We implemented new readout modes that were better suited for AO applications, and we demonstrated their usefulness for pyramid wavefront sensing. We use SAPHIRA for speckle nulling and also for speckle lifetime measurements. We observed the HIP 79977 debris disk with better resolution than previous near-infrared observations. We performed some color analysis and characterized its morphology. And then we also laid the groundwork for future developments, such as larger SAPHIRA detectors, its application at Keck and the Keck Planet Imager, and its application at several other observatories. And before I conclude, I would like to make one last argument for why I think I should graduate. I think this is the most compelling reason of them all, and that is my string of name tags accumulated in grad school now exceeds my height. So I'll take questions.
There is
Thanks.
space between the tags.
Questions? Yes, Nim.
On the slide with the data reduction of the HIP 79977 disk, the simulated board model, the simulated disk on the right-hand side seems to have circular annular regions. Can you explain what those annular regions are? Why does exist?
Yes. So as part of the ADI, we use basically we perform the ADI in this case it's 7 pixel increments. Essentially, it speeds the computation. We also have a version of this, which is this one down here, where we just did 1 pixel increments in radius. It looks better, but it's more computationally intensive. So for when we're running 20,000 models and trying to find the best ones, we go for this little chunkiness right here. It doesn't actually affect the outcome of the forward modeling. It just affects how pretty it looks. Yes. Anyone else? Barnaby.
I didn't quite understand when you mentioned that the cryo preamps had like a gain of unity. How does that help get rid of noise?
Yeah, so I have a plot, which I did not include in my bonus slides, where we connected an oscilloscope to the voltage from an individual pixel. And so this is sampling at a much higher frequency than the actual pizza box. And what happens is we clock onto a pixel and the voltage goes crazy and it oscillates and then it damps down with time. We have some settling time there and then we sample that pixel with the pizza box. And we want the pixel to have settled completely during that time. But in practice, it hasn't actually completely settled. And the preamplifier causes it to settle much faster. It's able to drive larger currents and cause the pixel to settle to a stable value much more quickly. And that's also why we could go to 2 megahertz from 1 megahertz, is because if we try to do 2 megahertz without the preamplifiers, we're just sampling crazy ringing in the pixels.
It's a matter of bandwidth. I guess.
Repeating myself in business.
Yeah. Which is, well, is it reasonably terminated?
Other questions?
Can committee members ask questions?
I think we're supposed to wait.
Oh,
Yeah.
okay.
Unless they're of general interest.
Ma'am, yes.
The 2.5 hour settling time for your detector, are there any practical ways to get around that? It sounds like it's something to do fundamentally with just the way that the inside the actual jewel, how it settles in temperature and stuff. It's got nothing to do with the readout itself, right? The readout electronics.
Correct.
So, can you think of any clever ways to try to get around that in the future?
Well, so this is not an effect that only affects SAPHIRA. This is having a lot of settling time is just good practice for infrared detectors in general. And so that's typically why you're just clocking your detectors all the time, or a lot of the time. So realistically, what you would want to do for a SAPHIRA application is start the detector idling in the afternoon before you go up to the summit, and then it's been going for 2 hours already by the time you're ready for actual observations. This applies to other detectors as well.